expansivity is the same thing. Cubical expansivity, we call it gamma. That's the symbol, gamma. For cubical expansivity, which is going to be change in volume. But we said for cubical expansivity, we are considering a body that have 3 dimensions: length, breadth, and the height. That is for cubical expansivity. So there is going to be change in volume over the original volume times change in temperature. And this we can also derive a function for change in volume, which is equal to what? The whole of this. This has cross multiply. Okay? And that's that. We can also get a value for the final volume. That is change in volume will be equal to final volume minus original what? Volume. Everything equal to the whole of this. So the final volume will be equal to, this one will now become the whole of this one plus V naught, which is original volume. V naught, which is original volume, is common. Let's factorize into this for temperature, then plus 1. And that's the expression for final volume. We can also get an expression for final temperature if we follow the same process of what we have done for linear expansion. Let's quickly see the relationship between the 3 types of expansivity. We have linear expansion, which is halva. We have area expansion or superficial, which is our beta. We have the cubical expansivity, which is gamma. We have a relationship between both of them. Our area expansion is equal to 2 halva. Our cubic expansivity, which is gamma, is equal to 3 halva. You have to take note of this. And right now we are going to take some questions and solve them. Question number 1. For question number 1, the question says a meter of volume 40 centimeter cube is heated from 30 degrees Celsius to 90 degrees Celsius. We are given original volume of that meter, which is 40 centimeter cube. And that meter is heated from, we have original temperature T0, which is 30 degrees Celsius. We have the final temperature, which is TF, which is 90 degrees Celsius. The question says we should calculate the increase in volume. What is the increase in volume? And that one is telling us to calculate final volume. And we are given a value for our linear expansivity. The value we are given is 2 times 10 is to power minus 5. 2 times 10 is to power minus 5 per Kelvin. The unit of linear expansivity is per Kelvin, or it can also be per degree Celsius, per degree Celsius, or per Kelvin from the definition of linear expansivity. So we are given the value of this. So this is simple. Let's quickly look at this. This question is about cubical expansivity, which is equal to this: change in volume, original volume, change in temperature. But if we look at this very well, what we are having here is gamma, not halva. This is cubical expansivity, but we are dealing with linear expansivity. So how do we now do that? You come back to our relationship. This cubical expansivity is equal to 3 times linear expansivity. Then we quickly look at this value of this which is equal to 3 alpha. 3 times, the value of alpha is 2 times 10. This is 2 times 10. This to power what? Minus 5. Which is equal to 3 times 2. 6 times 10 minus 5. And this is what we are going to use for our cubical expansivity. So let's substitute this one to our formula. We are going to have 6 times 10 minus 5 will be equal to change in volume. Will now be equal to final volume minus original volume. But our original volume has been given, which is 40. Put it there. Okay? Original volume again, 40. Then we have change in temperature. You can see the temperature change from 30 to 90. We are going to subtract 30 from 90. It's going to be 90 minus 30. Okay? So 6 times 10 is to the power 5 will be equal to VF minus 40. 40 times 60. Let's calculate the value, which is our final volume, by cross multiply. That's over 1. This times this times this. Okay? Which is equal to, we are going to have 6 times 10 is to the power minus 5 times 40 times 60. From there, we can calculate. Let's multiply 40 times 60. Okay? We can even calculate, we can even multiply it all to 6 times 40 times 60, because once we are operating with multiplication sign altogether. Okay? So as we are doing that, let's see what will be the value of 6 times 40 times 60 will give us 14,400, everything raised to the power minus 5. Okay? Let's see, so that the whole of this will give us, let's try and move 1, 2, 3, 4, which is 1.44. That is 10 raised to the power minus 1. Okay? But remember, we are looking for final volume, which is equal to 1.44 times 10 raised to the power minus 1 plus, this is minus. When it cross the bridge, it becomes what? Plus. Okay? So we are going to try and add this value together with this. 10 raised to the power minus 1 is 0.1. 10 raised to the power minus 1. That's 1 over 10. Which is, okay, let's see. 10 raised to the power minus 1. Let's try and evaluate this. We are going to have 0.1 times 1.4. You have to understand, this one alone is 0.1 times 1.4. 1.44, we have 0.144 plus 40. So let's add what we have here to 40. We are going to have 40.144 centimeter cube, and that's the final answer for the final volume. Question number 2. A wire of length 100 meters at 30 degrees Celsius has linear expansivity of 2 times 10 raised to the power minus 5 per Kelvin. Calculate the length of wire at temperature of 10 degrees Celsius. Calculate the length of wire. And if you look at that, that is final length. That is your final, because we have been given the original length, which is 100 meters at 30 degrees Celsius, which is initial temperature. So we now, what will now be the final length at this particular temperature, which is 10 degrees what? Celsius. So we are going to look at the linear expansivity is equal to final length minus original length original length, then times change in temperature, which is final temperature, minus original temperature. If you look at that question, we have been given the value for linear expansivity, which is 2 times 10 raised to the power minus 5 is equal to, we are to calculate the final length, and we have been given the value for original length, which is 100. This is also 100. Then for temperature change, we have initial temperature. So we are given the initial temperature to be 30, which is original, which are minus 10. Okay? We are going to have, this is minus 10 minus 30, which is 30. So let's try and evaluate. So we are going to have LF minus 100 is equal to, which is equal to 2 times 10 raised to the power minus 5 times 100 times minus 40. That's what we're going to have. Minus 40. LF minus 100 is equal to, let's try and multiply 2 times 100 times 40. 2 times 100 is 200. Okay? So we can quickly see what will be the value of 200 times 40. And what we are having here is 8,000. We are going to have minus 8,000 times 10 minus 5. Okay? So from there, we can quickly have, let's start with 1, 2, 3. This is minus 8 times 10 raised to the power minus 2. Then final length will be equal to minus 8 times 10 raised to the power minus 2 plus 100. Okay? So let's see what will be the value of minus 8